Thank you very much for coming. This is an honor to host you. So I want to say a few things about his background. So he was born in Racine, Texas. You want me to say that? So he has a college degree in neuroscience from the University of Michigan. And he holds a PhD in neuroscience from the Harvard Medical School. Actually, we just graduated in 2016. Congratulations. And then, but before that, actually, I want to mention that in November 2013, he was actually co-founder of a startup in Boston called WetLab. And WetLab was actually doing very cool tools in artificial intelligence. In just 1 year and 8 months later, so basically it was acquired by Twitter. And now Alex is part of Advanced Technology Group in Twitter. So the talk today is about automatic differentiation, the algorithm behind all deep nets. And please let's welcome our speaker today.
Everybody hear me okay? It sounds like it's fine. Okay, well, thank you for the very kind introduction. Yeah, so what was the word again? Omotenashi? Omotenashi. I think that's a really cool concept, so I'm glad there's a word for that, so I remember that. Cool, so today I'd like to tell you a bit about automatic differentiation, which is not just an abstraction for machine learning, but really the abstraction for gradient-based machine learning. And I'll tell you a bit about what that means. But a subset of that is neural networks. So this is a really fundamental idea, and if you really kind of dive into this idea, it really pays dividends for understanding all the stuff that's happening in deep learning, which is a subset of what's happening in neural networks, which is a subset of what's happening in gradient-based machine learning. It's a very deep, fundamental, shared concept across a lot of different ideas. So go past this in order to get introduced. I just want a quick shout out to Hugo La Rochelle and Brian Evans, who I developed a lot of this material with. And the first, I guess both parts are kind of a sneak peek to a Coursera course that I'm running with Hugo La Rochelle, which should be starting around January of 2017. So this is kind of the open beta of the Coursera content. So hopefully you guys give me some great critical feedback and I can improve this so that when it kind of goes online for people that aren't just here at this meetup, they're really great. So I'm looking forward to hearing your feedback. So the first part I want to talk about, just to kind of motivate the bulk of the content, which is to talk about neural networks in natural language processing. I'll give an example of one type of neural network that has been kind of flashy and part of the rising trend of deep learning in NLP, and I'll use that to motivate this idea of automatic differentiation. So the idea generally in NLP, or some flavors of NLP, is to turn some text, like this is a very good movie, into a bunch of numbers, and then to use those numbers to predict some label on that text. So this is one type of NLP that one might do, right? So the probability of this sentence being nice, in this case, my model that I completely made up is 0.93 out of 1. And what a disaster of a movie, probability of nice is 0.076, right? So that's generally the setup of things we want to do. Like this is sentiment classification, for instance. We also, at Twitter, we care a lot about topic classification. So is this about football? Is this about art? We also care about abuse and spam. So is this an abusive tweet? Is this a spam tweet? So they all kind of take the form of this, where we take some text, turn it into some numbers, and then we have a machine learning model which tells us if it's the thing that we care about or not. Right? So how do we actually construct those numbers? A really kind of first pass naive way that one might do that is what's called a one-hot encoding. And this is kind of a starting place for a lot of machine learning on text. The idea generally is I'm going to take this sentence, summer is over in Boston, I guess, and I'm going to normalize it. So you see things are lowercase, figure out punctuation. Summer is over in Boston, I guess. And then what you see is each vector, each word is now represented by a list of numbers called a vector. And I have a 1 in some locations and a 0 in others. and each row actually just has one on, which is called a one-hot representation. It means one entry is on. Right? And these columns correspond to words. Right? So if one is here, it means the word is yes. Right? So this is a really common starting place for a lot of NLP, is to make one-hot representation. So if I change the sentence, and also the size of the columns here is the size of my vocabulary. So in this instance, the only thing that my data representation knows about are these, I guess, whatever, however many words. This is it. So a typical vocabulary might be thousands or tens of thousands of words. This is a really small toy example. So if I change the text here, summer's over Boston, I guess, to bummer, summer is over, then now I only have 4 vectors that are on, and the ones are in different places. So this is a one, I'm just showing you 2 different examples of one-hot encoding of 2 sentences. There's a problem with this, and there's a lot of problems with this. But one thing that we might want to do is understand how similar words are to each other. So in a lot of modeling contexts, we might want to discover some automatically. So if we want to do sentiment classification, if I say something is nice and something is good, I don't want to have to lose all shared information between the words nice and good. I want them to be close together for some meaning of close. So things like subtracting the vector of bummer from the vector of summer does not equal, there should be a does not equal over minus summer. Actually, sorry, these are equal, right, which makes no sense. So these 2 words are as close together as these 2 words, because we have this one-hot encoding, and every single vector is exactly two apart, right? For every word in the language, it means every other word and every 2 words in English in this context are equally similar or equally distant. Right? So that's not something that we really want. So there was an invention in 2013, word2vec, which I think folks in NLP might have heard of, because there's some pretty impressive things that have come out of this research. It's been really pushed pretty aggressively by places like Google and Facebook as well. And the general gist is, instead of having words be one-hot vectors, you have them be dense vectors, so a collection of numbers. Right? So here I'm just showing maybe there's 2 dimensions of each word vector here, although in practice there's usually hundreds. And what's really interesting is there's these arithmetic relationships that hold up on words all of a sudden, where you learn dense vectors of words. So for instance, king minus queen is equal to woman minus man. Yep.
For us to wait with questions until the end.
But you can, yeah, interrupt with questions, please. Okay.
So I've heard of this. I don't know exactly how it works inside.
I'm going to show you in a second.
Oh, you are?
Yeah.
Okay. Isn't it all similar to LSI? Or is it...
Locally semantic hashes?
Yeah. I mean, that sort of puts words into a multi-dimensional space, although I don't think you could do any arithmetic on it.
Yeah.
It sounds like it's not helpful to think of this in the...
There's relationships, but it's maybe not kind of directly the thing that one might use here.
Okay.
So, what, there's other kinds of, those about making things plural. So kings minus king plus queen equals roughly queens, right? Which is pretty nuts, that you can turn words into vectors and then just add and subtract them, and the results actually make sense. This was a pretty big breakthrough at the time. So there's word2vec, which is this concept that's out there that people associate with these kinds of pictures. Word2vec is actually a family of models. There's 2 kind of main models that ended up forming the core of the first paper by Mikolov et al. In 2013. There's one called SIBO, or Continuous Bag of Words, and the other is called skipgram. I'm just going to focus on SIBO. But it really instantiates this idea, this quote that I really love, called "You shall know a word by the company it keeps." Right? The way I interpret that is, if you see a word, look right next to it, to the left and to the right, and you'll see other words that co-occur with it, right? So if I'm, looking at a zoology book, I might see the name of an animal and then the name of another animal, or the name of the verb of the thing that animal does, like ducks quack, for instance. You wouldn't see that in like a zoology textbook, maybe in a children's book. But you kind of get the concept that words that are related co-occur. They co-occur. You see them next to each other sometimes. So this model is directly instantiating that hypothesis about language, that nearby words can help inform the words that surround a given word can help inform what that word is. So the structure of this model is to take some word embeddings, so not a one-hot vector anymore, some list of numbers that we have yet to decide how we're going to learn, right? We're going to figure that out somehow. To take the words to the left, so 2 to the left, 1 to the left, 1 to the right, 2 to the right, and sum the vectors that represent those words. And then that should be used somehow to predict the word that I took out here. So that's the core idea behind SIVO. This is what lots of folks use to build word embeddings for doing sentiment classification, for doing abuse detection. It's really it's like a fundamental, it's a foundation upon which we do a lot of deep learning on text. Right, so before you can do any classification, you need your sentences to become numbers. And I'm not really going to get deep into how, once they're numbers, we make a prediction, but you can imagine training classic classification models like logistic regression or deep nets. But the idea generally is for a sequence of words, you need a fixed length representation of that sentence. So one thing people typically do is they take the word representation. So let me just kind of show you. So the idea generally is to end up with something like this, right? Where instead of all the words in my vocabulary being in columns, all of a sudden I have some arbitrary number of dimensions, usually around 200, and then the rows index into my words. So for a sentence, I might slice out, if I have a 3-word sentence, I might slice out 3 of these rows and average them, for instance. And that forms the numeric representation of my sentence. And then I can treat that like it was an image, or it was like ads data, or it was like really anything clinical data. It can be anything. Now I'm training a classifier. So the idea with a lot of deep learning and NLP is to very quickly get to the point where we're operating on numbers so we can kind of do traditional machine learning stuff. Does that make sense?
The row is the sentence?
Pardon?
One row is the sentence?
One row is a word. So I haven't told you yet how to combine words in sentences. I'm actually not going to have time to talk about that today. But this is generally the strategy, is to turn words into vectors and then come up with another aggregation scheme. And there's a lot of different styles for turning lists of words into a single vector.
So one word has the number of digits, and the number of numbers equals to the number of dictionary, right? To the size of the dictionary.
So we're replacing a dictionary with some dimensions that we've learned. So instead of this being word 1, word 2, word 3, or dictionary, this is now just arbitrary dimension 1, which might mean something or might not, arbitrary dimension 2, arbitrary dimension 3. These are being learned and they're really difficult to interpret. The general idea is now a word, instead of being just a string of characters, is a fixed length vector of numbers. And what each of those dimensions mean is usually kind of a mystery. But the point is, you can add and subtract 2 vectors and then look for the word that is the closest to the result of that, and it actually ends up making sense. Right? So that's this idea of king minus queen is equal to man minus woman. So the idea is we're moving words into this high-dimensional space in which operations make sense.
When you refer to that word vector, that's added across whatever you're turning version of word vector, or is that specific to your subset of dictionary?
That's a good question. So the dictionary rows are words, right? So there's often a token for unknown. So just like, I don't know what this word is. If you download word-to-vec embeddings from so Stanford has a version called Glove. If you download the Glove embeddings, you've got this huge corpus of like 20,000 or 30,000 words. What you do in practice, if you have the resources to invest in really solving a text problem, is you retrain word-to-vec on your text corpus. So at Twitter, we retrain it on Twitter data. We have our own word-to-vec embeddings, and we have our own Glove embeddings that are specific to all the kinds of words and phrases and stuff you can find on Twitter. Does that answer your question?
So, does linguistic style, like suppose instead of active voice I use passive voice, would have any effect on the bit vector representation?
So that's a function of sequences of words. And certainly if your corpus that you're learning this on prefers one style or the other, that will certainly affect the embeddings. However, it really only gets a view on like single words. So if you use passive versus active voice, it's going to be more than one word constructing that particular style. And that's just not going to show up here. It will show up when you build models on top of these things, which is a topic that I think we could have 3 meetups about that, about how to do that.
so you may get to this, but I'm guessing that the process by which you construct these 200 dimensions, and thus the process by which you end up projecting each word into these 200 dimensions, is actually completely ignorant of the identity of these tokens as words.
Completely.
They're just arbitrary labels.
Yep. They're actually just, the words are turned immediately into indices.
Okay.
Yep.
Right. But no, the important thing is that basically the same word occurring in different places will still map to the same place.
Exactly.
That's really pretty much the only.
The hard part, and I'll highlight it just kind of in a very small way, is the hard part is bookkeeping, right? You just turn all of your words into these integers that
So if I may just put this up, is the fact that you can do this now, famous, king minus queen and so forth, was that part of the design? Did someone think that would happen, or was it kind of a lucky break?
I don't know the answer definitively. The impression that I've gotten kind of being around folks that do this is that that was a pretty surprising feature. That was, so at the very least, it was a huge selling point of that paper.
No kidding.
Yeah, it was very, very surprising to the field that you could do that. Whether or not they designed that explicitly, I think this was done at Google, and I'm sure there was a lot of iteration that ended up at this, where they might have gotten a hint of that.
Right.
But I don't know the story anymore.
Okay.
It's clear that I would imagine that most of those operations, they were going to be made necessarily some sense. I would say k minus 3 equals to atom minus 1.
Yeah.
And so there's no word, right?
Maybe not, yeah.
So
what's literally happening there, what the operation that's happening is you're doing vector subtraction, and then you're blending at a place in word space, and then you're going and you're looking at the word that's closest. So that's what's happening. So it's not actually giving you, we're not translating right back from those numbers to a word. You're looking up what the word was. So if there's nothing in that space, or nothing within some radius, then yeah, it's just a relationship that doesn't exist for that particular word. And that might be a tool that's interesting for linguists to exploit, for instance. Like, are there gendered, kind of culturally gendered equivalents of words that we might not have originally suspected were there? That's an interesting question to investigate. Yeah. Also, these are random numbers, right? This is totally cartoon. So, how do we actually train this? The goal is, so let me just show this picture again. We have the words 2 to the left, 1 to the left, 1 to the right, 2 to the right. And we want to use those to predict the word in the middle. So this isn't exactly actually not what SIBO looks like, but the flavor of what you want to do is you want to make this quantity small. So say you have some words and index them by I, and there's some vector representation for them. I want the difference between the middle word and the sum of the words around it, I want it to be small. And so, how do I go about doing that? And this is not the real SIBO loss. But SIBO is kind of like a tiny little neural network, right? It's taking vectors and it's adding them, multiplying them with stuff. And every single neural network that you're going to run across, except for ones that are very, very old or ones that are extremely new and kind of experimental, but 99.99% are trained with back propagation. Right, so you'll hear this a lot. Trained by neural net with back prop. Or reverse mode autodiff is another sound that you'll hear. So the way back propagation works is it uses derivatives. And what that means is that I want to know how my loss changes, so how this difference goes down if I change the parameters. So if I change the word vectors slightly, how does that affect the distance between affect my loss? And I want to change my parameters just enough so that this error goes down over time. Right? You need derivatives to do that. And back propagation uses the chain rule of calculus for computing derivatives. It's just a mechanical way of getting these derivatives. And kind of answering the question of how the error is going to use if we change our vectors. So backprop is really fundamental. And that's kind of what I really want to talk to you about for the rest of my time here. So I want to take a step back first and just emphasize that computer science and just doing any kind of numerical work, or really any work on a computer, runs on stable abstractions that we should take for granted. Right? I'm not going to reinvent the concept of an array. That That was done for me in 1957 by the Fortran programmers. I'm not going to reinvent the concept of factoring a matrix or of doing a matrix vector product. That was done by Glass and Limpack and Lomback. And it actually took them like 20 years to figure out just the right way to phrase these operations on a computer. It's a very, very slow process for developing some of these incredibly fundamental ideas. The idea that if I'm programming a numeric routine, I shouldn't have to re-implement sine or cosine or x or some other functions. This idea that I should have all the common subroutines available to me, that really as a concept wasn't around until like the mid-80s. Now I've kind of solidified that in the numeric programmer's consciousness. And this is really popularized in the open source world by NumPy. So machine learning has other abstractions. Of course, it builds on those, right? They're fundamental. We can't get rid of those. We really need to just actually forget about them. They're that fundamental. But machine learning has an abstraction that's still kind of developing in the sense that we're still figuring out how it should be implemented. We're in the middle of that 20-year Lomback period right now. And that abstraction is called automatic differentiation. And this is a quote from Rob Perlmutter. He's a really wonderful machine learning researcher that thinks about this as a research topic. And the definition here is of autodiff, so you hear me call it autodiff a lot, is that it's a way to mechanically calculate derivatives as functions expressed as computer programs. Right? So I'm not, with pencil and paper, doing a derivative of some function I've written down. This is, the input is a computer program, and the output is a new computer program that gives me gradients. And it does it at machine precision with complexity guarantees. So another way to do this, the original way people tried to train neural networks is using something called finite differences, where if I have a 10-weight neural network, and I have some desired loss, and when they go down, I take weight 1, and I move it up, and I see what happened to the loss, and I move it down, see what happened to the loss, right? And then I use that to take a step in a direction. And then I do it for the second weight, third weight, fourth weight. There's a lot of problems with this. It's algorithmically very expensive, and it also tends to have big issues with numerical precision. Right? So this isn't actually going to give you the right derivative when it's implemented on a computer a lot of times. It's a really bad idea to train neural networks with finite differences. And symbolic differentiation is the kind of thing you'd either do with pencil and paper, or you do it in Mathematica or Maple. The problem with symbolic differentiation is if you write down the equation for a neural network, and maybe it's this big, when you say, give me the derivative of this, in Mathematica, it takes up a whole page. Right? So these expressions can really, it's called expression swell. So using symbolic differentiation is often not a good idea for these types of applications. And this idea of autodiff has been rediscovered a bunch of times. That's a review paper that kind of goes into the sordid history of the people that claim to have invented it the first time, or really just stumbling upon their ancestors. I think the first implementation that I would call modern autodiff, the kind that takes in a program and spits out a new program, was done by Bert Spielbenning in 1980 in his thesis. And this is kind of like a Bobby Fischer character in the sense that he wrote this thesis that founded this field. It's a small field, but founded a field nonetheless, and then disappeared. And he went off to top math, and he's a very happy person. And apparently he resurfaced recently at this autodiff conference. It was like, really like Bobby Fischer coming back to like a chess conference or a chess tournament. So he's kind of an enigmatic figure. I think that's kind of cool. I think every idea should have an enigmatic figure that's associated with it. I think that adds legitimacy to a set of ideas. In neural networks, it was not invented but popularized by Rumelhart as backpropagation. So you hear backprop. That is a very, very kind of highly used term in neural networks. It's the same thing. This has actually been in heavy use in nuclear science and other kinds of simulation fields like fluid dynamics and climate simulation. And in fact, and they don't talk to us machine learning people, but we don't have a dialogue with these people. But it's a shame because their automatic differentiation tools are on the whole, a great deal more sophisticated than ours. So actually, that's a bit of an aside, but I think we have a lot to learn from kind of our intellectual cousins in these other numeric fields. And I want to clarify that the version that we use in machine learning is not just autodiff, it's a specific kind called reverse mode autodiff. There's two extreme styles of autodiff. One is called reverse mode, the other is called forward mode. And I'll show you this in a couple different ways of what the difference is and why you actually want to use that for training neural networks. So here's a forward mode schematic representation. So as with many deep learning tasks, the input is often pictures of cats, and the goal is to move these cats through these neural networks and predict whether or not this is a cat. Right? And right now I have 4 classes, and my neural network is not very good. It thinks that this is mostly a dog and kind of a little bit of a cat. And I want to correct this, right, by showing us billions of pictures of cats, because I work at Twitter and had access to billions of pictures of cats. I could do a couple different things, and the way that I'm going to compute the derivative, and the way to read this guy basically is, I want to see what the effect on my loss is, which is, the difference between this one and the vector, right? Can you hear me? How about now? Oh, okay, great. So I want to see how the loss changes if I fiddle with the parameters at each of these layers. So that's the goal. And that's what the gradient. Might be low on battery, so I'm just going to check. Can everybody hear me in the back? Okay, great. So there's 2 ways that I can calculate this gradient, which we know from the chain rule, I can just decompose into these pieces. Right? One way is to go from the left to the right. Right? That's really bad. It has bad computational complexity. Also, each of these things that I'm doing are these big matrix-matrix products. You want to never do a matrix-matrix product if you can get away with it. It's the computational complexity is cubic in the size of the matrix. So that's bad, right? I'll show you another reason why it's bad. But I'll do this in kind of program form. So what I'm going to show you is a trace of this kind of trivial program here. And a trace is just which functions were actually run in a program. Right? So you won't see any if statements, you'll just see these arithmetic functions being run. So as I go down this function, I say A is 3, B is 2, C is 1, and then now I'm going to evaluate one of these if statements. Turns out I ended up in this branch of the if statement, and I've evaluated this output value D, and it's sine of B. So how do I get the gradients of this? How do I get the effect of changing A on D? So the way you do this in forward mode is you start off with A is 3, and then you define this kind of nonsensical gradient how do you change the change in A with respect to A, which is always 1. Right? If I change A, I'm going to change A the same amount. Then I find B, and then I find the derivative of B with respect to A. It's not dependent on A, so it's 0. As I do run each piece of arithmetic, I can also calculate the partial derivative at that point. Right? At the very end, I get dd dA. Right? So what's happening is I need to eventually get dd dA. I'm incrementing the kind of the numerator of this partial derivative. So that's kind of how forward mode works. The problem is if I want dd dB, so if I want the derivative of d with respect to b for some reason, I actually have to run this whole thing again. And that's the reason why forward mode is a very, very bad idea for neural networks. For each parameter, you either need to run the program the number of times for the parameters you have, or you need to expand your memory by the number of parameters that you have. So if a neural network has what's typical is tens of millions of weights, it means tens of millions of times of duplicated either effort or wasted memory. So it's really a non-starter. But it is useful in some cases, just generally not in machine learning. But I want you to be aware of this because A, people don't tend to talk about it. B, I think it puts reverse mode in context. And C, if you ever kind of get into these ideas, you want to be aware of it so that when it is appropriate to use it, you know what it is. So that's the program view and symbolic view of forward mode. So reverse mode is what you'd expect, which is I'm going to go the other way. And this is great because I'm doing these matrix vector products. And matrix vector products are a lot better than matrix products. And the computational complexity is a lot better. So in this program trace, something different is going to happen, right? So I'll define A, B, C, I'll run my program, so I run my program in forward mode. When I'm doing the gradients, when I'm getting the gradients in reverse mode, I'm going to actually have to run my program all the way through. Right? Because remember, we're going from right to left, so I need the results of my program before I can start getting the gradient. And you'll notice I instantiate, instead of dA, I have dd. So what I'm going to do is I'm going to build this partial derivative by decrementing the bottom part of this partial derivative. Right? And I can do that because I have all the information that I need to return that. So what this means is if I want to DB, I actually have all the information that I need at that point to do that. So that's why it's really good to do reverse mode with neural networks, is if I want to do, instead of just parameter 1, if I want to do all the other, 10 million minus 1 parameters, I can do it in one sweep. So this is why people use reverse mode autodiff, and they just call it backprop. So we have implemented kind of our opinionated version of this Twitter in a package called Torch Autograd. And we use it a lot for training neural networks, both for research and also at scale Twitter. And this is what an entire neural network looks like. So this is equivalent to some things that we actually do use in production. Right? So it's just one page of code, and this is both the definition and the training code to run a neural network. Right? There's not a lot of cruft in it. You can actually see all the guts and see what's happening. Right? So we can define our parameters, which is just going to be some numbers. And then here's our neural network function, and this is what's actually going to make predictions. And neural networks there's not a lot going on in them for kind of the vanilla kinds, where I'm going to take my, say, image, multiply it by some weights, and then add a bias, and then apply a nonlinearity, so here just a tanh. And then you just do that again, feeding in the results from the previous layer. And then usually you turn it into some probabilities or something like that. But that's a neural network. That's the whole thing. And then the loss defines how good our neural network has done at any given example. Right? So usually that's you run the neural network, and then you take in some true label, and you compare them somehow. Right? So this is also kind of small. You don't need to remember the details. The idea is these are usually one-liners for even complicated things. And this is kind of the entire API of autograd. You import it. This is in Lua code, not Python, which I think most people are familiar with. We use Lua a lot at Twitter. And what you get out, when you call this function grad on this function, is a new function. So that's what autodiff is. Autodiff takes in a function and gives you a new function. Instead of returning what the original function returns, you now get the gradients of the loss with respect to the parameters. And that's exactly what you need to update the parameters of a neural network. Right, so here's our training loop. Right, so for every data point in our data set, and I made this up. It's usually, you got to work on that. I'm going to call this dLoss function that I got with the exact same signature as the original loss. What was being returned are the gradients. And the gradients are the same size as the parameters. And if you want to update parameters, there's a fancy word for it, it's called stochastic gradient descent, but basically it means turn down the gradients a little bit and subtract it from the parameters. Right? These are the same size. And that's your update. Right? If you do this hundreds of thousands of times, millions of times, you have a trained neural network. Right? So this is the entirety of it. All the magic of autodiff lives right in there. Right? So that's the thin interface to turning this from just some, originally predicting totally random stuff, clicking it in with stochastic gradient descent, and actually learning to make useful predictions. So what's actually happening underneath the hood? So the way we actually do this automatic differentiation process is we listen as functions are being run. So we replace all the functions in our numeric library in Lua, so that's called Torch in Lua, which is like the equivalent of NumPy in Python, for instance. We replace every single function, also multiplies and minuses and sums and raising things to the power, with kind of secret spy functions that listen to the arguments that are coming in, run the original function, keep track of what was run, and then return the result. So as we run this function, we record that W and input we're using to multiply, the result in B we're using in add, target and the result in add we're using sub, and so on and so forth. So we build this computational graph. And this is the record of the arithmetic that we've done that we need to then get the partial derivatives of. Right? We do this, I'm not going to go into the details, but we do this with operator overloading, like replacing the functions with kind of listener functions. And then when we actually want to get the derivative, the gradient of the loss with respect to the parameters, we actually have to walk back and calculate all the partial derivatives, right? It's going from right to left in reverse mode autodiff. And how do we know which partial derivatives to use? Well, what we've done as developers of the library is just to find the partial derivative of every single function you can run in Torch. That way you don't have to worry about what you can differentiate or not, or pass gradients through or not. So we've kind of done all that work behind the scenes. So here's some examples of things you can do, of things you can kind of turn into little toy neural networks, basically. So this one's really simple. You're just going to add A to B times C, and you can get the results back. Right? So this is something you could probably get the gradients of by hand and pencil and paper in, 30 minutes, or for me, 3 hours if I had to go back to my calculus textbooks and remember how it's done. I'm so dependent on autograd to give me gradients now, I can't really do it by pen and paper very quickly. So I'm really dependent on this kind of mechanical process existing in the computer. What's really interesting, though, is you can begin to intersperse and control flow. So this is something that TensorFlow has a very hard time doing. This is something that Theano has a very hard time doing. This is something that basically every neural network library, besides autograd and its kind of intellectual cousins, have a very hard time doing. It seems silly, but this is basically a non-starter for a lot of stuff. So you can add in if statements and it just works. And I've been showing you yeah.
What does it return as singularities?
Yeah, so that's a great question. So the question is, if B is right on top of C, you introduce this discontinuity. That's actually an open research question, how to automatically deal with that. The way that you tend to deal with that, if you really are crossing those boundaries a whole lot, is you build in differentiable versions of this, right? So you might actually say, I'm going to evaluate both of these and blend them according to how close B is to C. So that's typically a strategy one would use if indeed those discontinuities introduced issues like numerical precision or your network didn't train. However, that often is not the case. So usually I just write it in a naive way. If I go through some diagnostics or through some debugging, that's actually a problem with crossing the boundaries of time. There's strategies for kind of smoothing the if statement boundary. Does that make sense?
It's really kind of the secret sauce to think of that you have to take possession of the numbers. You kind of keep things at the level of computation.
Yeah, I would elaborate that one a bit, and I'll go into the differences between all these neural network libraries, but the secret sauce is that we let the language tell us what the compute graph looks like at runtime. So we do just-in-time evaluation of what the compute graph is. With TensorFlow and Theano, you need to say, here's my graph, then it can't change. And that's true with really every other library. So we listen in and figure out what's... So the graph can be different every evaluation, every sample. We don't care. For loops, also a huge inconvenience in Theano and TensorFlow. They have this construct called scan, which is extremely difficult to work with. You just write a for loop, right? Super easy. But this is getting a bit kind of fancy and maybe not applicable, but you can write every for loop as a recursive function. So here, I've got my f of a of b. If b is 0, it's my stop condition, return a. Otherwise, call f again with some changes to the parameters. Right? This does the same thing as the for loop. And because we don't define the graph ahead of time, we just listen to what gets run, this works just fine. Right? I think you'll be hard-pressed to find any kind of production-level neural network libraries give you this kind of flexibility. Yep, there definitely is. And that's something that we addressed with kind of a more restricted optimized mode. So what will happen is we'll cache the compute graph contingent on the inputs. So all this control flow is contingent on the inputs that you pass in. And so if those inputs stay the same, then the graph will stay the same. So oftentimes we'll have if statements switch on single scalars that mean do this thing or do that thing. So we'll actually cache the whole compute graph and just look it up again. So there's kind of compiler-ish strategies for getting around that idea. Yeah, so the optimized mode will effectively do that. That's kind of like a special case of what we do.
Don't have if you have training functions for the derivative,
Say it one more time?
if you have changing derivatives as you move through the parameter space, doesn't that pose you on the GPU?
Do you mean changing definition of my compute graph?
Can you repeat the question?
But yeah, the question was, if I have changing gradients,
Yeah.
that makes GPU computation difficult. So I guess I don't understand the question. Are you referring to like the just-in-time nature of autograd, or are you talking about something different?
The calculation for the gradient is going to change as we move through the branch space, depending on which branches you take.
Oh, so you're talking about branching specifically. Yeah, so usually each of these operations, like a matrix multiplier or convolution, are extremely compute heavy. And so the data is already in the GPU, and you get almost full GPU usage if you're using NVIDIA's special matrix multipliers or convolutions in a library called cuDNN. So if you do a lot of tiny operations and your graph is changing wildly from iteration to iteration, yes, there's a slowdown, right? Static graph is something you can optimize. In practice, this isn't the case because each function run is usually really expensive. So each layer of a neural network is a really big matrix vector multiplier. And that ends up being something that kind of takes up the whole GPU. So in some cases, yes. In almost all practical cases for large neural networks, no. So, yes.
The last slide. The function f is a to the power of b. What is it?
Yeah.
And then if b is 0, so it becomes 1, right?
If b is 0, then it is 1 because a to the 0 is 1. Yeah, that should return 1. Sorry, you're right. There should be another statement there.
But if b is 1, then you return, then you go to the
Yeah, it should be if b is 1.
Yeah, anything is the power of 0 if you want. And the AA, if b equals 1, that.
If I had a t-shirt, I'd give it to you. I only have half a sandwich.
Okay.
You have to plug in the code.
Okay. Yeah, I just want to understand what the.
Yeah, no, it was meant to be a translation of this one.
Okay.
I didn't do it very well, apparently.
Yeah, I used to work with the mathematics.
Oh, got it. Yeah, it's kind of like Lispy style, which I'm not super familiar with. Very nice. So this is something that's a little bit weirder, but kind of highlights the flexibility and power of autograd. So a kind of a mini project that an intern at Twitter Cortex or Twitter ATG embarked on was to differentiate through the JPEG compression algorithm. So to create a neural network that could learn to compress JPEG images better. Right? We didn't finish this because we switched to a different project, so if any of you want to do it, you should do it. So differentiating through JPEG is mostly easy because there's all these kind of functions for which we've got partial derivatives for, but there's one step which is really hard, which is a quantization, right? Which means numbers less than some value are set to 0, and that's how you compress things, right? You get rid of information. So a floor operation, which is a quantization, has a gradient of 0 everywhere except for sharpness continuities at number values. So how do you actually back off through this? What people tend to do for functions like this is they just ignore it, or they come up with some continuous approximation. But usually you just kind of say, actually the gradient is not 0, it's just 1, and that ends up working pretty well. Neural networks tend to be pretty robust to bugs like that. That's technically introducing a bug. But neural networks tend to be pretty robust to stuff like that. So you can often get away with it in practice. I'm not going to go into the details, but the gist is basically that you can replace the gradient. Yeah.
So can you also use this as an automated approach to the reparameterization?
Yes, you can. So the question is, can you use this as an automated approach to reparameterization tree? That is a reference to a technique that's used to be able to backpropagate through sampling from random functions. So if I depend on some random numbers that are generated in my neural network, how the heck do I backpop through that? There's a way of rewriting how you sample those numbers such that the random parts just pop totally out of the function, and the rest of it is arithmetic. So you just have to write, so if you're sampling from a normal Gaussian instead of sampling from, some mean and standard deviation, you sample from 0 to 1, and then you multiply that to move the scale. So you kind of have to write your own reparameterization trick, but we will take care of the derivatives. Does that make sense?
Yeah, so can you do that through a internal?
Yeah, completely. And that's kind of what message passing. So you can train with gradients for sure. You can also train like HMMs with message passing. That ends up being like kind of related to taking gradients. But yes, you can. Sometimes maybe that's not the best. give example, like totally problem dependent. But yeah, you can't. So, and then just demonstrating here that once you use your special redefinition of floor, you can actually take gradients through something you previously couldn't take the gradient through. So that's kind of the whirlwind tour of the weird things you can do with autograd. We end up using it. It kind of reduces our prototyping time, so we use it a lot for weird ideas. We just try it out in an afternoon. If it works, it works. If it doesn't, it doesn't. So, popping up the stack a little bit, what makes all these different neural net libraries so different? So why do I want to use autograd? Or why would I want to use, scikit-learn, or Torch, or Keras, or any of these guys? And I think they're different along a couple different axes, and I kind of just want to give you a high-level overview of what I think makes these things different. So the first thing is the granularity of operations available to you as the user of the library. So in scikit-learn, for instance, you get the whole model or you get nothing. And so they have defined, however many models. And if you like that model, that's cool. If you don't like that model, too bad. Right? Then there's these layer-based approaches like Torch NN and Keras and Lasagna. So people, I think Keras is pretty popular these days for neural networks. What they give you is they give you whole layers, right? So a linear layer, like that's the kind of the stock vanilla layer in a neural network. That's really just a multiply and an add, but you never see the multiply. You never see the add. In fact, you have no access to it, right? So that's slightly more granular. And then there's libraries that do full auto-diff. So you can use any arithmetic function that you want, compose them in any way that you want, and you can still get the right gradients. And so autograd does that, Theano does that, TensorFlow does that. So that's one axis along which these neural net libraries are different. And the reason why they're different is because the developers decided to expose different partial derivatives, right? So these are kind of not like a Lego block, it's like little nubbins. These are basically the nubbins on the Lego blocks for you to be able to click these things together. This is like Duplos, this is like this, right? And then this is just, I don't know what this is. Other pieces of plastic, I guess, the plastic toy, whatever you want to use. So this axis also, this organization also helps think about the difference between neural network libraries along another axis, which is kind of how they end up actually doing their computation underneath. So on the far end, like autograd, Theano, and TensorFlow, they actually implement what I described, automatic differentiation. They're the engines. And the guys in the middle almost always use an engine to do their neural networking stuff, but they only expose the layers. Okay? So they're auto-diff wrappers. And then there's these kind of shrink wrap models, right? And Andre Karpathy, who's a neural net researcher at OpenAI, has a really great way of phrasing which one you should try. So if you're doing something that other people have done, so if you're trying to classify images or you're trying to classify text, his quote is, "Don't be a hero. Use the ones that are really easy." So if you know that what you're doing has been solved by other people before, go just grab a model that is already pre-trained, use Caffe, use something like that, but download somebody else's code. You don't need to be all the way over here, right? This is fun for me. I like this stuff. But if you're trying to solve a real problem in practice, if I'm just classifying images, I don't work at this level. I work at this level. So another way that these neural net libraries are differentiated is how this compute graph is actually built. So I described autograd, and we build it just in time. So we listen to all the functions that get run, and then we build a compute graph in a just-in-time fashion every time you run that function. So we're there sitting and listening when you do multiply, add, subtraction, square, all that stuff. Right? So this is one approach. It's actually one of the rarer approaches to building compute graphs and neural networks. And there's kind of like 3 general styles of building graphs. So the first is very explicit, where you actually write down in a config file or in a static piece of code, this is my graph, it's memorialized for all time, it's not going to change. Right? So NN and Caffe fall pretty squarely in that bracket of, I'm going to tell you the graph before the code is even run. Ahead of time graph compilation is something that TensorFlow, I think, borrowed from Theano. Theano was kind of one of the original, really great neural network libraries out there. TensorFlow is kind of subsuming it entirely, kind of consuming that space. And the idea is you tell a runtime. You say, hey, here's the order of operations that I'm going to do, and you're telling the runtime to listen and compute and construct this graph. The graph gets constructed and frozen, and then it gets run somewhere else. Right? So you're kind of building the graph in software at a runtime. And there's just-in-time compilation, which is what I described with autograd. Chainer is another library that does this as well. And there's actually a couple different flavors of autograd. So the original version is in Python by David Duvino and Dougal McLaurin and Matt Johnson. This was out of Ryan Adams' lab. Right, so if you want to see the original stuff, you can go look at the Python autograd. So that's how the graph was built, and kind of what order and at what time during the life cycle of the neural network. But there's many different types of graphs. Right? It's not, the graph is not just lines connecting dots. Sometimes the lines and dots actually have meaning. And people talk a lot about data flow graphs in neural networks. And the definition of a data flow graph is actually pretty restricted. It means that the nodes are functions that are stateless, and the edges are data. So if we think about the graph types that these different neural net libraries use, there's differences between them there. So static data flow, which means that I'm using a data flow graph, but the graph is static. That is, anything happening like before. JIT data flow, right? So we're building a graph that's just computation. That's autograd and chainer. TensorFlow and Theano don't actually, I've been kind of trying to get this out of the developers. I know it's true for Theano, and I'm still trying to speak with people on the TensorFlow team to verify this, but it is true for Theano. The graph type is a hybrid. Right? So the graph type is not just data flow because they need conditionals and for loops to be in the graph. And then the runtime has special knowledge about that graph that it can then interpret. So what you have is really not actually any kind of well-defined graph type. You've got this kind of hybrid, what I think is kind of a hack. So there's this other graph type called sea of nodes, which really elegantly merges control flow and data flow. Nobody's done anything with it. So I think that's an open problem in neural network libraries, is to try to use these types of ideas. So if you want to go write a cool neural network library, I'd encourage you to go think about that. So there's a lot of different styles, there's a lot of different approaches, but really, we don't want any limits on what we have to write. Like I said, I don't want to have to be a hero. If I'm doing image classification, I want to take a big convolutional neural net, just use it. If I'm doing crazy research stuff, I don't want to be limited by having to use one network type or one layer type. I want to do anything, right? So we designed autograd to be able to go across all those different boundaries. Right, so I'll show you like a neural net in 3 different ways, and then we'll conclude pretty swiftly after that. So here's the most granular way. This is a wall of text, but the take-home is I'm defining all the parameters individually, and I'm doing every single piece of arithmetic by hand, right? So this is like really down in the weeds, kind of like, Brooklyn hipster, bespoke, custom-made fixie neural network, right? This is like super custom stuff, right? Usually what I'm doing is I'm working with layers, right? So a linear layers are multiply and add, and convolutions, kind of like a multiply, but special. And so I'm usually just going to say, hey, give me all these layers that come from the Torch NN library, which we've wrapped, and then I'm just going to use those layers in order, right? And then for kind of stock stuff, I'm just going to say, hey, give me a whole neural network. I'm just going to use it. Right? So autograd kind of hits all these different levels on the abstraction hierarchy. In other libraries, you kind of have to punch through abstraction barriers to kind of do the work that you want. In autograd, there's a very nice flow from very, very abstract in general, kind of use the whole neural network down to the individual arithmetic operations you want to do. So it's very easy to cross those boundaries. So back to the SIBO idea, and this is a little handwave because it's not exactly what you want to do, but this would, in a sense, do something. It's like, this is the function for training SIBO. Right? So you take grad of SIBO, and then you train it on all your words. Right? So that's the code that you'd write for this kind of naive implementation of SIBO. It really should be that simple. If you have an idea that you can turn into a mathematical or numeric expression in computer code, you can train the parameters in that expression by just calling grad of that function, and then doing some gradient descent. So it really has simplified our development process because we don't have to worry about doing the partial derivatives and calculating the gradients. Like it's kind of like grad student work, which I'm very familiar with, having recently graduated. But I'm not a grad student anymore. I don't do that. So I use autograd. The impact of Twitter is kind of to sum up this kind of prototyping without fear. So we try crazier stuff. So in some of our image models, instead of having just a bunch of class labels like car, truck, duck, cat, dog, we have a taxonomy. Right? So if my neural network guesses car, but the correct answer was bus, those both fall under the taxonomy of vehicle, and so it gets partial credit. It's called a tree loss. And it's really a pain in the butt to write if you're doing it by hand. But autograd makes it trivial to do it. So we tried that out in an afternoon, seemed to work pretty well. And I'm not sure if that's still in production, but that was like a model that was taken seriously internally for a while. We also did image captioning in kind of a weekend because these made models so easy to write. There's other kind of crazy autodiff ideas out there for people that are interested in this as a concept. One of the things that I think is could have the most impact is this idea of checkpointing. And the word checkpointing is usually used in terms of saving the model off every couple of epochs. This is not that concept. This is separate. This basically refers to discarding intermediate computation to save memory, and then on the backwards pass, recomputing it. Right? And I won't go into the details, but the effect of that means you can train models that might be 40, 60, 80 gigabytes in size, so we're talking billions of parameters, but you can fit it on the card because you've done this checkpointing process and reduce it to like 4 or 8. So MXNet, I believe, is the only neural net library that implements that. We want to follow their lead. And they have examples in a white paper that's pretty cool if you're interested in those ideas. Mixing forward and reverse mode. So I said forward mode is bad. Forward mode is not always bad because you can mix forward and reverse mode. That's something that really doesn't exist anywhere in neural network libraries right now. Stencils kind of refers to doing weird stuff with images, and we need to get better at training neural networks on extremely weird image operations. I think there's some interesting research that's going on there. Mostly through Stanford by a guy named Zach DeVito and a group led by Pat Hanrahan, and then some work from Brian Gunter at Microsoft. Source-to-source transformation is an interesting idea that used to be the gold standard for performance in autodiff, like in the 80s, when people were doing like nuclear physics simulations. You take the whole source code and you read it like a compiler would, as opposed to running it, which everybody else does. Like all neural network libraries, including autograd, run the code in some form. So in source-to-source, you just read the code, and then you spit out a new piece of text, which is a new program. Basically, it's a compiler. And that ends up in the reason why you want to do that is you have access to the graph, and you can do pretty crazy graph optimizations. People haven't done that in a serious way with the modern language. I'd say maybe we're 10 years behind in terms of when the last person tried this in a serious way. To my knowledge, it's never been done for neural networks. So it'd be kind of interesting to see what that looks like. And then in the higher order gradients, so if I take grad at F, what happens if I take grad and grad at F?
And I want to have something out of the box. I don't want to program anything at this, let's say, first stage. What could you suggest?
So Andre Carpenthy has a really great blog post called The Unreasonable Effectiveness of Neural Networks. And there's some code you can download where it will digest a bunch of text, and then it will dream new text. So you can feed it Shakespeare, and it will just spit out kind of funnily good Shakespeare. You can feed it Java code, and it feeds you back Java code. And I don't like Java, so I like to kind of just paste that into my review boards and Twitter. So just give them fake neural net generated Java code. So you can feed it any kind of text and then try to mimic the style. So you can just download that code like a command line tool.